All right, you think. So anyway, this is Hikari, if you don't know him. Not only does he have like the schwankest, spikiest hair you've ever seen, but he's also damn smart. How's that for an introduction?
Sounds good. Hey, everybody. Thanks for the introduction. Yeah, so my real name is David Hulton. Some people here like to call me Hikari. I'm the chairman for Toorcon, and I also do lots of security R&D with FPGAs and stuff. So I've already talked about some of the things I'm going to be covering today. There's actually a lot of things here, and I'm going to skim through as much as I can. First of all, how many people here have seen me talk before? Anybody? Okay, a few people. How many people here know what FPGAs are? Yes. Sweet, okay. So I'm just going to skim through all stuff. As you can see, there's a lot of new things I'm going to be demoing. And I'll probably skim through a lot of the explanations just so I can get to the demos. So first of all, FPGAs are a bunch of different gates that you can just hook together however you want. It's actually a chip, and you can design any sort of chip design, upload it to the chip, and it'll function like that chip. So you can design your own processor, you can design your own graphics accelerator. In my case, I'm designing basically a chip that cracks crypto and uploading it to these chips that we have and cracking crypto with it. And when you have dedicated hardware like that, you can do things a lot faster. So this is kind of what a chip looks like. This is a Vertex 4 LX25. And it has different things like input-output pins, slices, which are general purpose sort of areas of the chip that you can configure however you like. There's DCMs, which are clock multipliers that let you change clock frequencies and stuff. Kind of like the jumpers on the old school motherboards to set your speed. Block RAMs, which are kind of like cache. They're storage elements inside the chip. There's these DSP slices that are used for doing multiplies and additions and really high-speed sort of math calculations. And then all the different sort of components in here you can connect together with the programmable routing matrix, which lets you connect anything with anything else on the whole chip, which is really what makes the whole thing work properly. So first of all, I'm going to be covering this program called Anybody heard of that? Airbase? Yeah? Okay, a couple people. So Airbase is actually written by Johnny Cash, and it's a re-implementation of AirCrack and also like a brute force web cracker that actually supports distributed network cracking, kind of like distributed.net, where you basically have a server and a bunch of clients out there, and you can feed out jobs to crack web by brute force. So it also contains a bunch of different tools that are for manipulating web file captures and stuff. So you can check all this stuff out by yourself. But essentially, it's all the same tools that you see with AirCrack and with any sort of standard web cracker. This is what JC AirCrack looks like. It has lots of cool ASCII effects and stuff. This is JC WebCrack. There's a daemon in the client. And we also have a Pico client, which is our FPGA accelerated client. This is kind of what a screenshot looks like. I'll be doing a real demo of this later. And yeah, basically the daemon has clients that connect to it. With our Pico client, we just attach an FPGA to it and offload the web cracking to one of our cards. And there's lots of different ways that you can do this. With JC AirCrack, one thing that Johnny actually did was he has this library that does all the RC4 cracking stuff, and he actually implemented Pico support. And so as long as you use this library, it'll just automatically use the Pico card, and or automatically use what machines you have and stuff. Oh, Pico card is one of our FPGA cards that we design. But you can take any sort of FPGA development board if you like and use that. Here's actually one of them I can show you. Verilog? Yeah. So this is our Express card. It's a module 34 size Express card that's plugged into this laptop. We've also got a compact flash one and a card bus one. So basically, Airware is made so you can just plug in arbitrary hardware, accelerate your algorithms, and just use it and not have to worry about the actual thing that's doing the computation. And actually, Johnny was saying that HDM threw together some RC4 acceleration for the PS3, so it actually uses the hardware units on there to do stuff. I'll show you some performance numbers on that later. So this is kind of the whole tool suite. You can look at it more later if you like. Web cracking basics. All you do is you sniff a packet. The first few bytes are predictable, so you XOR that to get the actual output of RC4 for a given key. And then from there, it's basically just taking the output of RC4 and reversing it back into the key. So my design actually uses either 32 or 48 custom RC4 cores. And so I have a ton of little RC4 cores running on the chip, and they just do RC4 really fast and try to reverse that back. So essentially, your input is this K over here in RC4. I don't know if you can see my pointer. And then the output is the PRGA, and so it's just reversing that back across. So yeah, it's a total brute force attack for this implementation, and then also JC Aircrack does that attack for doing the statistical sort of stuff. And yeah, essentially, we have a key generator where you tell it, okay, start at this key and end at this key. It starts sending out keys to the RC4 cores, gets the PRGA back from them, and then checks to see if it's the right value or not. And so it gets a bunch of PRGA back, and then eventually it actually finds a matching PRGA and says, okay, here's the actual key that corresponds to that. So it's fairly straightforward. One small optimization that I do is in RC4, there's this whole initialization phase that takes a really long time. And that can actually be done in parallel with all the other operations. So that's one optimization. You can look at the code later if you want to see exactly how all that works. Then performance numbers with this is with JC Webcrack, and typically like just running RC4 on a machine, you can get maybe about 300,000 crypts per second. With the PS3 client that HDM threw together, using all the 6 SPUs, you can get about 1.4 million per second. And with our little compact flash card, you can get about 12 million per second. And we also sell clusters of them with like 15 that'll get you about 180 million. And how this relates to actually cracking a 40-bit key is that on a PC it takes you about 42 days. With one of our cards in a laptop, you can do it in about 24 hours, so a little over a day. And then if you have a cluster of multiple ones, that brings the time down quite a bit. And with the PS3, it takes about 8.8 days to break 40-bit.
Hey David, are those numbers 100% of the key space or 50% of the key space?
That's 100%, the full 40 bits. So yeah, like if you're talking about like birthday paradox sort of stuff, then it'd be maybe about half that. So Pico Webcrack is basically the JC Webcrack D plus Pico cards and some cool matrix effects I'll be demoing in a little bit. And also a new release that Johnny just threw together is JC Aircrack with Pico support, so I'll be demoing that as well. See if this switches over. Yeah, okay, cool. All this stuff you can download off of opencyphers.org, by the way. So this is the web brute force. I just threw together some scripts here, typing with one hand. Yeah. This is a pretty small key, so won't take too long here. So this is actually starting up the daemon right now. And then it'll start up some Pico clients. Because this actually has 3 separate cores that it's talking to that each have 16 RC4 cores, there are 3 different instances running here. And it actually just found the key on one of them, which is a pretty simple key. But that's going at about 9 to 12 million crypts per second right there, and it just found it. I don't have too much time, so I did a pretty short demo for this one. And now I'm going to show you the Aircrack stuff real quick. So, here's, I'll show it to you without the FPGA support. So this is running, this is using the FMS. Oh, can you see everything? I lose video? Oh, there we go. Okay. So right now it's doing the FMS attack with just JC Aircrack, and it's chugging along. This will probably take a little while. So as you can see, it's doing maybe about 1 chunk per second, maybe a couple chunks per second. And I'll just cancel it now because I know it's going to take a while here. And so now with the FPGA, now it's doing about, how many chunks per second? Maybe 30 or 50 or something? Or, yeah, so it's already gone through, 733 chunks, and the last time it took maybe about 10 or 15 seconds to go through, like, 50 or 60. And there's some cool animations too, so. Okay, there we go. So it's basically just like aircrack, but now you can accelerate brute forcing the last bytes with an FPGA. So let's switch back over. Now I'm going to switch over to this other laptop because all my other demos are going to be done in Windows. Some new support I threw together. Hopefully this Vista laptop will work. It actually helps my demos look a little bit better because it's so slow that all the software runs slower. Let's see here. Mirror displays. There we go. Okay. Hopefully my slides will work here. Try restarting this. Oh, does it have a stupid thing? Yeah. Okay. All right. There we go. Cool. Okay, so I'm going to skim through the WPA stuff. Essentially, for added security with WPA, when you actually type in your passphrase in Windows to log in, to your WPA access point, it actually hashes it with PBKDF2, and then it actually uses that as your key for authenticating on the network. And the reason for doing this is because they just wanted to have a really good secure transform from your password into an actual, secure key. And PBKDF2 essentially just it runs SHA-1 about 4,000 times, and so it takes a really long amount of time to actually compute this PMK value from your passphrase. And so their hope was that because it takes so long to do that, every time you try to convert over a real passphrase to a PMK value, it takes forever, and so somebody attacking it would take a really long time to actually crack. So essentially, all I do is I just accelerate the PBKDF2 phase using 8 SHA-1 cores, and essentially this is the performance comparison that I get. With Cowpatty on pretty top of the end P4 Intel Core Duo, you get about 60 or 70 per second. On one of our FPGAs, like our Compact Flash one, you get about 430 per second. And with Aircrack, you get some optimizations, maybe about 100 per second on a PC. So it's maybe about 4 to 6 times faster than a PC, roughly. And one thing that we did last year was we took a huge word list and kind of created a rainbow table. It's salted by the SSID, but we took the top 1,000,000 words and the top 1,000 SSIDs and created this huge table, thanks to RenderMan. And finally, we have this 40 gig, whole thing of pre-computed values up, and we should have it up. Cool, okay, yeah, so talk to RenderMan if you want to get the 40 gigs, or you can grab them off of BitTorrent, thanks to the Shmoo group. And I don't think that they're actually posted on their page right now, but if you do a torrent search, you should be able to find them, according to Hult. So here's a demo of Cowpatty with FPGA support and some Perl scripts to glue it together. Oops. Oh, no idea. Check. Come on. Oh no, did I lose my screen? Oh wait, there we go. Okay, sweet. Oh no. Okay. Oh, here we go. Okay, resize some of these. So all this stuff runs under Windows now. If you want to actually run Cowpatty under Windows, you can grab these binaries if you want. And this actually works with both of our cards with like our E12 or E16 or whatever. Oh man. Here, I'll show you it without FPGA support. Oh yeah, so that's kind of the usage for just running it normally. Right now it's chugging away really slow here. And so actually, I'll go over here and do it at the same time with one of the Pico cards here. I've got this handy batch script here. So that's it running on the FPGA on the right and running on my computer on the left. And this is actually an Intel Core 2 Duo, like about 2 gigahertz or so. So it already found it and went through 4,000 keys, and this one's still on 1,800 or so. So it's obviously a little bit faster. Oh, yeah. There we go. Okay. Now, how are we doing on time here? 5 minutes till Q&A. Okay. Next thing I'm going to talk about is File Vault. How many people use File Vault on Mac OS? Yeah? Yeah, a few people. Okay. So Apple has this cool explanation of File Vault. Secures all your data by encrypting it with 128-bit encryption. This high-performance algorithm automatically encrypts and decrypts in real time, so you don't even know what's happening. The only problem is that we wanted to know what was happening. So essentially, it takes your home directory, stores it in a DMG file, and they basically embed the crypto stuff into the drivers, and it automatically mounts it and does all of the encryption and decryption on the fly from this DMG image. And there's a couple different versions of it. You can read the source, and I think that we've got some more presentations that go in more depth, but do some research if you want to learn more about it. So the cool thing is that it actually uses PBKDF2 for the password hashing. So it was really simple to port over my WPA stuff. I was actually at the CCC and managed to get everything ported over in like 24 hours from the time that somebody told me that it used PBKDF2. We presented on it the next day. But yeah, it's pretty simple. It just uses 1,000 iterations instead of 4,000. And I worked with Jacob Applebaum and Ralph Philip Weinman on doing all this stuff. So, yeah, they ended up throwing together this program called VF Decrypt. We called it Vile Fault because we didn't want to have any sort of copyright problems with Apple. So I hope that they appreciate that we took that into account. They actually didn't want to write a File Vault cracker, so they wrote this program that just decrypts File Vault images that are encrypted. And so as long as you have the right passphrase, you can feed it into this program and it spits out a clean DMG with no encryption. But how do you find out the passphrase, right? So I just modified their source and hooked it up to one of our Pico cards. And so this thing will actually take a word list, run it through and find the right passphrase for your File Vault image. And some other attacks that we figured out is they actually don't specify that the memory shouldn't be swapped out to disk. And so if you can somehow use up a bunch of memory in the person's PC, they should swap it out to disk and you can read it from there. There's also hibernation problems. A hibernation file will contain their passphrase and their key and stuff. And possibly with ring, you might be able to read it. The weakest link, though, it turns out that the RSA key that they use for the version 2 header actually is easier to crack than the 128-bit key. And also the Salted SHA-1 password that you use for your login is the same password that they use for the File Vault image. So you probably want to just fire up their password file into John the Ripper if you have access to that, because then you can use the same password for decrypting their image. So here's some performance comparisons. It's pretty similar to attacking WPA. Top-of-line machine will get about 180 to 200 per second. On one of our FPGAs, it's about 2,000 per second or so. So here's the demo. Let's see if I can get this right. Okay. And this you can also run without an FPGA if you like. Oh yeah, here. So I've got this batch script here. you just give it a dictionary file in the DMG image, and so this is it running without an FPGA. And this is it running with the FPGA on my laptop. So there, found the passphrase. Cancel that. Okay. Now, last thing I'm going to talk about is Bluetooth pin cracking. There have been a couple other people that have done stuff like this. There's these people that wrote a paper on it that you can download off the internet. Just Google for it. And also, another person, Theory Zoller, wrote his own implementation of this. So you can use mine, or you can use a bunch of other implementations. Essentially, Bluetooth uses the Safer Plus algorithm and uses it for pretty much all the things they do. And so basically the exchange, it's very similar to WPA in that you have a bunch of data that goes across the internet to exchange keys and verify that everybody has the right key. But the only thing that you don't really have is a pin. And because the pins are actually just numerical digits most of the time, it's a really small amount of key space that you have to search. The maximum is basically 10 to the 16, which is still fairly small. And most people don't actually use the characters, and most people will use like either 4 digits or 8 digits. So I basically implemented Safer Plus and then wrapped around the stuff around that to implement their other specific algorithms that are used for the key exchange. And this is essentially the pseudocode for doing the whole thing. You can look at it more later. But but here's all the values, and we're just brute forcing the pin here. Is that for me? No. Oh, okay, all right. So essentially, one safer algorithm here, and then I just loop the output into the input and start swapping out these different algorithms and just basically muxing the whole algorithm. And the pin generator is done on the FPGA, so it keeps it really fast. And once it actually finds a pin, it just says, okay, this pin matches, so it backs it up and figures out, okay, that's the correct pin for the whole thing. This is actually super fast. On a normal PC, it does about 40,000 per second, which means for a 4-digit pin, 1/4 of a second. It takes about 42 minutes for an 8-digit pin. On one of our cards, we can do about 10 to 15 million per second, which is a few hundred times faster. And an 8-digit pin only takes about 10 seconds. And I'll show you this in a minute. After this, I'll pretty much be done.
I'm going to get uncomfortably close to you until you stop.
Okay, all right.
There's also a bug that's up here.
Oh, sweet. Is that a prize for somebody asked a good question? Okay, so this is cracking one of these capture files that I have on my PC here. And so this script is supposed to go through 6 different captures that I have, with some that are like 5 or 6 digits long, some that are 8 digits long. And so this is it running on the FPGA. Wait. Huh. Why isn't it working?
I don't want to go to the next step.
Ah! Okay, let me pop this out and pop it back in. See if that works. Okay, there we go. The first one it cracked in a split second. This next one is an 8-digit one. It cracked in a split second. And there we go. It cracked all 6 of these in about a total of 5 seconds. And the other one, it'll probably take about a few hours. So there you go. And I'm just going to skim through here real quick.
What? No.
No? Okay. Wait. Go into the conclusions here. There we go. Okay, questions? Anybody?
What the hell just happened?
Okay, so our compact flash ones, we just came out with our newer Express card ones. So the compact flash ones we're discounting to around $2,000. If you want, we're doing a show special for about $1,900. $1,800. And then for our Express card one, it's going to be around $19,000 to $2,000 or something like that. So.
Have you considered the manufacture of ICs based on FPGA designs to sell them at a lower cost?
Manufacturers of ICs?
You're modeling an IC with your FPGA. That's what you're burning the fuses.
Yeah, yeah.
Consider just actually producing ICs off of those.
If you can find enough people that want them, we could probably do that. Yeah, but you wouldn't be able to swap around, what programs you're using with it. Oh, okay, sorry.
It still doesn't do it.
Yeah. Well, yeah.
Yay, let's hear it for Hikari. Yeah. So he is about the most understated individual I think I know that gives these kind of talks, because he'll be up here and be like, this is kind of cool. And boom! Here's this thing that's 100 times faster. You're like, is that really? Oh my God, it is 100 times. No one else is kind of reacting though, so I'll just sit here and watch him quietly. It's like, my Lord, I've been in a couple conferences where we did that GS